All right, thank you, Ed. So coming into this workshop, we assume that many of you are already experienced with mass spec. If you aren't, I highly recommend taking a look at some of these useful references that we've listed on the bottom left. If you're watching this recording, and you're not live, but you're watching this recording and you don't know anything about mass spec, I encourage you to pause and take a look at some of these references, and then come back to the workshop. But here I give you a abstract or maybe even minimal introduction to EI mass spec, and really from the perspective of a data analyst or a data scientist with very limited chemistry background. So here I've presented a chemical structure of fentanyl, and you'll notice that the color of the structure is black to indicate that it's neutral. Fentanyl has a molecular mass of 336 daltons, and because we're at NIST, I should specify daltons as grams per mole. All right, so we have a molecule. In electron ionization mass spectrometry, the molecule is bombarded by electrons, and in this high energy state, it might fragment. And part of the molecule may hold on to the charge. We call that a fragment ion. In this case, the red part of the molecule. That fragment ion has a mass of 245. And there's a neutral part of the molecule that has fallen off. We'll call that a neutral loss of 91. Of course, that's one example of where a bond might break. It may be that the ring opens up and then you have a charge on one part, but now giving a fragment ion of 189 and a neutral loss of 147. Of course, the ring may break in a different part of the ring, and also the charge might be on the other part of the molecule, resulting in a fragment ion of 132 and a neutral loss of 204. Or the molecule may not fragment at all, and then this is a very particular type of ion that we call a molecular ion that can be quite useful for diagnostics. In this case, the molecular ion would be 336. Of course, in mass spec, we're not doing single molecule analysis. We're looking at a sample of multiple molecules. And so what a mass spectrum really is a histogram of ions in your mass spectral analysis of how ions are distributed across mass to charge ratios. Another way to think about it, and this is a lot of the way that us mathematicians and data scientists think about a mass spectrum, is as a signature, a fragmentation pattern that we can use to as a property of a molecule. So it's important to note, and this is why I kind of started with this very brief introduction, is that each of these clusters of peaks should be explained by a structure. So in this example, I actually show a mass spectrum of hexane. And so this cluster of peaks around 86 are representative of a hexane molecular ion. This cluster of peaks around 57 are representative of this ethyl loss and this four-membered fragment ion. But what I want you to take away from this, and it's interesting because I showed you fragmentation of fentanyl, and yet I showed you a spectrum of hexane. Not all molecules are this easy to explain. Not all mass spectra are this easy to explain. And so to kind of summarize everything I just said there, the mass spectrum is a measure of mass to charge ratios of ions formed during the analysis of the sample. And so usually our EI mass spec follow GC, and so our sample is a pure compound, or our analyte is a pure compound. And the ions can be representative of complete molecular structures, so we call that a molecular ion, or substructures that we call fragment ion. This is an important message to take away. The mass spectra are easy, and I say that loosely. They're easy to explain when the structure of the sample is known, much harder to interpret when you have no additional context. And I kind of liken this to working on a puzzle. So if you've got a puzzle and the lid, the box that your puzzle came in, and you see what the photo or what the puzzle is supposed to be, you can piece things together pretty easily. If you've lost the box and you don't know anything about about what the puzzle is supposed to end up being, it becomes a lot harder. Of course, also kind of to stick with the puzzle analogy, some puzzles are easier to put together than others. If I've got a 10-piece puzzle, I probably don't need the box. If I've got a 1,000-piece puzzle, the box becomes essential. So mass spectra are pretty hard to interpret if you don't have any additional context. But one excellent source of context is mass spectral libraries. All right, so what is a mass spectral library? It is a collection of evaluated reference mass spectra for known compounds. The first EPA NIH mass spectral library was published in 4 volumes by the National Bureau of Standards, which is what NIST used to be called, back in 1978, and it contained reference mass spectra for 25,000 or more than 25,000 compounds. I show the covers of the 4 volumes and like one page from, I think, volume 1 or maybe volume 2. I should have also showed you the other angle so you can see how thick these books are. They're quite impressive to look at. They're big phone books of mass spectra. Of course, this is how things were done in 1978. Now we are a little further along, and so we actually produce these libraries as digital databases. We produce many libraries in the NIST Mass Spectrometry Data Center. That's actually the data center that I work in, and us and some of our collaborators publish several mass spectral libraries. An important one to this seminar or to this workshop is the NIST EI Mass Spec Library, which is a commercial library. Also important to this workshop, and I probably should have highlighted in bold, is the NIST GC Retention Index Library. We also assist the Scientific Working Group for the Analysis of Seized Drug in evaluating their mass spectral library, which is free for download at swigdrug.org. We produce a DART mass spec library with Ed Cisco's group, which has in-source collision-induced dissociation mass spectra for several drugs, cutting agents, things of that nature. And we also produce a tandem mass spec library. And yeah, like I said, they no longer come in these volumes of books. Although I was thinking it would be fun just as just as kind of a fun thing to do, to print them all out in paper. We'd end up with probably 50, 60 volumes, but yeah, that might be a waste of a forest. But yeah, now we sell them in CDs, or of course you can buy them as digital downloads. All right, so the 2 libraries that probably won't come up too much in this webinar, but I just want to quickly mention is the NIST Tandem Library. So this is MSMS. You can kind of see the distribution. There's a lot of metabolites, and this library is primarily used for metabolomics type analyses. And then, of course, the DART library is a drug library, but this is for if you have ambient ionization mass spec capabilities in your lab. Both of these libraries can be used with NIST MS Search, which is a program that I'll highlight in just a couple minutes. And the DART library also comes in a R data table format to use with one of our new software tools, the DART Mass Spec Data Interpretation Tool, which was specifically designed for handling DART mass spec data. And yeah, the big library that will come in handy with this webinar is the NIST EI library, which has over 300,000 compounds as of NIST 2020. And maybe if we get a chance, Ed Arisman might tell us a bit about what to expect in the next release. But yeah, so around greater than 300,000 compounds. And many of these compounds also have retention index values, which come in the GC Retention Index library as well. So along with these big libraries of evaluated mass spectra, the NIST Mass Spec Data Center also produces several algorithms and free software to help you use this library. In particular, we produce AMDIS, which is the Automated Mass Spectral Deconvolution and Identification System, NIST MS Search, NIST MS Interpreter. Oh, sorry, and MS Search is the screen grab you see right here. NIST MS Interpreter, and the DART Mass Spec Data Interpretation Tool, which again won't come in handy in this particular workshop, but just good for you to know that we do have that available as well. And all of these software tools are free to download, and they're all available through chemdata.nist.gov. So MS Search, our biggest piece of software, and maybe the most central piece of software. This is kind of the big engine of our suite of software tools. You can do a lot of things here. It gives you a lot of opportunities to interact with a mass spectral library. You can search your library for compound names, molecular formulas, particular fragment ions if you're interested, substructures or structure searches. But importantly, you can also search an unknown or a query mass spectrum against the library and try to find the most similar spectra to your query in the library, or multiple libraries as well. I should mention that MS Search allows you to upload not just NIST libraries, but other commercial libraries or even user libraries in NIST format. It's just very basic, similar to my basic introduction to mass spec. I want to give you a very basic introduction to library searching. So with any mass spectral library search algorithm, the first thing is we have to take our mass spectra, which are paired mass to charge ratios and relative intensity values, and put them into some type of format that a computer can understand. And usually we do this as some type of vector. And in this case, our blue mass spectrum is a query. That's why we denoted it here with a vector Q. And our library mass spectra are in this yellow box right here. And we've denoted this with vectors LA through LC. The next step is that you have to compute some representative similarity between the query and library mass spectra. You do this just for generalization. I use a function f, and I feed in my query, my library, and potentially some other information about our spectra. And then we compute a similarity score, in this case SA, SB, and SC. And then the final step in this library search process is you have to interpret the results. Generally speaking, when the library search algorithm returns the results, it returns them in an order of decreasing similarity. That does not, and I emphasize that, does not imply that the first entry that's returned to you is your unknown. It may be any one of the top few hits, and so it requires some human interpretation and inspection of the results. So to summarize, given a library of mass spectra for known compounds, the identity of an unknown compound can be proposed by comparing its spectrum with spectra contained in the library. There are a couple of obvious limitations for any type of library search algorithm. The first is that the quality of the spectrum representing the unknown in the library must be similar to the quality of the query mass spectrum. So if your query mass spectrum has, or maybe the better way to say it is that the quality of your query mass spectrum has to be similar in quality to the spectrum of the library, or the spectrum in the library. And so, if your query mass spectrum has contamination, if there's unnecessary grass peaks, that can really throw off your similarity computation, which will then potentially give you deceptive results. And so one of the things that we have to kind of combat this limitation is the automated mass spectral deconvolution and identification system, AMDIS. I'm not going to go into the details of AMDIS because I'm sure you'll see it get used throughout this workshop. But the general idea is that we're able to deconvolute the mass spectrum by ensuring that we're only extracting peaks that make sense by looking at the ion chromatogram. And again, I won't go into the details here because I'm sure it'll come up later. But AMDIS is available for free at chemdata.nist.gov. Oh, and also importantly, spectra, you can extract mass spectra using AMDIS, send it directly to MS Search for identification, or if you're doing some routine work, it may be that you can actually just identify or search your compound right, or search your spectrum right in AMDIS with a couple of simple searching tools that will also potentially yield you fruitful results. So it's kind of a good place to start your mass spec interpretation processes in AMDIS. All right, the second limitation, and this is not just for mass spectral library searching, but this is really any database search, is that your correct identification requires that a spectrum of the unknown actually exists in your library. If I'm using an English language dictionary and I'm looking for a Spanish word, I'm not going to be very successful. And so this is important that you have a library that is comprehensive, that has everything that you need. We have a couple of software tools to help with this limitation. And actually, before I go into the software tools, the big thing that we're doing for this limitation is we're constantly growing the library. And so if you're looking for a query and you feel like, oh, there's nothing in the NIST mass spectral libraries that helps us identify this query, shoot us an email, let us know, because it may be that we need to expand our library in that direction. We might be missing a class of compounds that we would benefit from adding to the library. But beyond building the library, which is painstaking work, we also have some software tools to help with the identification of compounds that may not be in the library. And those are the hybrid search and MS interpreter. So very briefly, what the hybrid search is a search option within NIST MS search, and it allows you to match spectra with a reference spectra, or match your query mass spectrum with reference mass spectra that differ by peaks that are shifted by this parameter that we call delta mass, and this is the mass difference between the two compounds. And the cool thing here is that when you use the hybrid similarity search, a high score implies that your unknown differs from your reference compound by a modification that affects only a single branch of fragmentation, and so this manifests itself as a shift, a very predictable shift in the mass spectrum. And that gets you that really gets you 60% of the way there. If you know that your compound, your unknown, differs from a library compound by one modification, and you know the mass of that modification, you've really made a lot of progress in your ability to identify that unknown. But further, we have this tool, MS Interpreter, which is really powerful. It allows you to interrogate your mass spectrum with the potential structure and try to explain possible peaks in the spectrum with that structure. So yeah, this is a real powerful tool. And again, I think that many of our speakers will at least reference it. And so I look forward to hearing what they have to say. And also this tool, as with all the other software tools, are available for free, downloadable at chemdata.nist.gov. So far, I've kind of highlighted all of the tools that we produce at NIST. But what's important to recognize is that these are all tools. So I only got into mass spec in around 2016. And one of the first papers I read, and I was struggling with this because I come from a math background, and I was like, oh, what's going on with these library search results? You know, I think I know what I'm looking at, but then it turns out I don't. And so I found this paper in my readings. There's a perspective article in JASMIS about identifying EI mass spec library search results, or evaluating EI mass spec library results. And in the concluding section, the author, David Sparkman, says, people, not mass spectral library search programs, identify compounds based on mass spectral data. The library search program is only a tool used to help in these identifications. So he wrote this in 1996, and this idea still persists till now. We have many more tools, and they're much more powerful. But at the end of the day, it's still people that have to make these mass spectral, or make these identifications and make these calls. And so that's why this workshop is actually not really about the tools. I've shown you all the tools, and you can always find literature about the tools. But what we're excited to share with you are some people using these tools, and not just any people, but experts in the field that have used these tools, among other tools, for years. And so with that, I'm going to pass it on to Ed to introduce our star-studded lineup.
Thanks, Arun. Maybe before we jump over there, we had two questions that popped up during your presentation. I think they're relatively easy to answer, but the first one is, do I buy the libraries directly from NIST?
No. So no. The quick answer is no. There are distributors that sell the library. We have a list of distributors on chemdata.nist.gov, but you can shoot us an email and we'll let you know who is available to buy. And actually, you know what? I shouldn't answer this question. David Sparkman will be a good person to answer this question, and he will maybe be able to speak on this later.
And the second question was, what instrument company data files does AMDIS read?
Also, this is an answer I should know, but I don't know. But luckily, we have some experts that will be able to answer this in the next couple minutes.
So I'll bring those back up when Ed and Gary speak.
Perfect.
Awesome.